Hi everyone. Welcome back to Dave's Math Channel. I'm your host David Tear, and I just got back from vacation in San Francisco last night. I think I told you guys I was going to be gone for 10 days. Well, I just came back. So anyway, today I'm gonna conclude my series on limits. This is a subseries of calculus, and I only have one more type of limit to discuss, and those are limits at plus or minus infinity. And you can see on this graph I show here, here's a function, this is the function f of x equals x over x minus 1. You can see that it has both a vertical asymptote shown in green, and it has a horizontal asymptote shown in blue. And it's the horizontal asymptote we care about for this case. We want to see what happens to this function as x approaches infinity or minus infinity. And, as we'll see, the function does have a limit in this case, a limit of 1 in both cases. But anyway, before we do that, let's define the limits at plus or minus infinity of a function. So we say that a function f of x has a limit L at infinity if for every epsilon, every positive number epsilon, we're supposed to imagine epsilon small here, there exists a positive integer n, which is supposed to imagine as large, such that whenever x is greater than n, we have the absolute value of f of x minus L less than epsilon. That just means that f of x is approaching L. It gets the difference in the absolute value gets less than epsilon for significantly large values of x greater than some large value n. And similarly, when the argument's negative, we just say that that limit is L if for every value of x less than minus n, the absolute value of f of x minus L is less than epsilon. So it's kind of like the other definitions we were doing. But anyway, let's just do an example. So let's consider this example again. Here's the function f of x equals x over x minus 1. And we want to prove that both limits, the limit as x approaches infinity and minus infinity of f of x are both equal to 1. So how do we do that? Well, we just use the definition, and it's pretty straightforward in this case. So let's let epsilon be some small number, arbitrary positive number, and let's let capital N be 1 plus 1 over epsilon, which is going to be large when epsilon is small, obviously. So then let's see what happens when x is greater than n. Well, in this case, you can just calculate f of x minus 1, which is going to be positive in this case. It's going to be x over x minus 1, which you can work out. That's just 1 over x minus 1. And since we're letting x be greater than n, that's just 1 over n. That's great. Less than 1 over n minus 1 because it's decreasing. And that, by definition, is equal to epsilon. So we've just proven, at least for the case, for the case where x goes to infinity, that the limit is 1. And the case where the limit goes to minus infinity is very similar. This time we just let x be less than minus n. Basically the same calculation, we just invert things. Here we're calculating 1 minus f of x, because f of x is now less than 1. And if you do that, you'll get 1 over 1 minus x, which is less than 1 over n, which was equal to epsilon. So again, we've proven that the limit as x goes to minus infinity of f of x is equal to 1 in this case. So that proves both cases. And that concludes my video on limits and infinity. And I think you'll be happy to know that at least for now, we're done with limits, and now we can get into some more interesting stuff involving derivatives where we're actually doing calculus. Derivatives do involve limits, that's why I had to go through limits. But now it'll get fun, and I think it'll get easier. So thank you for watching. Long live math, and I'll see you guys next time.